Let's discuss the alternating series, absolute and conditional convergence. Up to now, we have focused exclusively on series with non-negative terms. In this discussion, we will discuss a series that contains both positive and negative. To start, let's have the alternating series. The series whose terms alternate between positive and negative is called alternating series. Example for that, you have 1 minus 1 half plus 1 third minus 1 fourth plus 1 fifth minus so on. Okay, and it could be a negative 1 plus 1 half minus 1 third plus 1 fourth minus 1 fifth plus so on. So in general, an alternating series has one of the following two forms. The first one, you have the summation of the quantity negative 1 raised to k plus 1 times a sub k from 1 to infinity, which is just equal to you have an a sub 1 minus a sub 2 plus a sub 3 minus a sub 4 plus so on. And the other form is you have the summation of the quantity negative 1 raised to k times a sub k from 1 to infinity, which is just the same, or which is just equal to you have negative a sub 1 plus a sub 2 minus a sub 3 plus a sub 4 minus so on, where the a sub k are assumed to be the positive in both cases. So by this we have theorems in which it is a key result on convergence of alternating series. Okay, so let's have this one theorem. An alternating series of either form 1 or form 2, which is the what I have discussed in the previous slide, converges in the following two conditions are satisfied. The first one, it must be you have increasing monotone, and you have the limit of a sub k, or k approaches to positive infinity, is equal to 0. Okay, so let's have this example. So you have used the alternating series test to show that the series converge. So in this case, okay, we could have for our solution, okay, now in this case, uh, we know that our a sub k is equal to uh, 1 over k, okay, which is, in this case, we know that it is less than 1 over k plus 1, because if you substitute this one, if this is 2, 1 half is greater than 1 third. Okay, remember that this 1 over k plus 1 is our a sub k plus 1. And in this case, the first condition is satisfied. We can now say that this is increasing monotone. Now the second one is you have the limit of our a sub k, where k is approaching to positive infinity, must be equal to 0. Now if we are going to substitute this one, you have the limit of 1 over k, where k is approaching to positive infinity. Okay, clearly this is equal to 0. Therefore, we shows that the given is convergent. Okay. Another, you have the summation of the quantity negative 1 raised to k plus 1 times k plus 3 all over k times the quantity k plus 1 from 1 to infinity. So in this case, let's try to see if this is increasing monotone. So we're going to apply the ratio. We can apply the ratio here. So you have our, okay, a sub k plus 1 over a sub k should be less than 1. Okay, in this case, uh, we are going to add here. You have k plus 4 over k plus 1 times k plus 2 all over our original. You have k plus 3 over k times k plus 1. So simplify, you could have, we can divide out this one, and then in this case, you have k squared plus 4k all over the product. You have k squared plus 5k plus uh, 6. So in this case, if we are going to substitute any number here, let's say 2, okay, or even 1, if this is 1, you have this is 5 over, you have 5, 6, that's 6, 12. Okay, so you have 5 over 12. Clearly, that is less than 1. Therefore, we can say that this is increasing. Okay, another is you have the limit. Okay, so the limit of a sub k as k approaches to positive infinity, which is equal to the limit of our k, which is k plus 3 all over k times k plus 1, k approaches to positive infinity. So in this case, we could have divide numerator and denominator by the highest degree. So you have that's equal to k squared. So you have the limit of you have 1 over k plus 3 over k squared all over 1 plus 1 over k as k approaches to positive infinity. So which is equal to, this is 0, this is 0, 1, 0, so 0 divided by 1 is equal to 0. Therefore, we have proved that the series is convergent series. Okay, so let's have approximating sum of alternating series. Okay, so the theorem is concerned with the error that results when the sum of an alternating series is approximated by the partial sum. So we have the theorem: if an alternating series satisfies the hypothesis of the alternating series test, and if S, okay, which is the sum of the series, then the sum of the series lies between two successive partial sum. That is, either you have the sum is equal to, you have less than or greater than or equal to, you have the first partial sum, but less than the next, uh, less than or equal to the next partial sum. Or you have the sum is less than or equal to the next partial sum, but rather the s is greater than or equal to the next partial sum, but less than or equal to the partial sum, depending on which the partial sum is larger. And if the sum is approximated by the partial sum, then the absolute error of uh, s minus s, the sum minus the partial sum, satisfies the absolute value of the sum minus the partial sum, which is less than equal to the next element in the sequence. So, moreover, the sign of the error, the sum minus the partial sum, is the same of that of the coefficient of the next sequence. Okay, so let's have the example. Example number 2, find the an upper bound of the magnitude of the error that results if the natural logarithm 2 is approximated by the sum of the first 8 terms in the series. So you have there, okay. Now in this case, okay, we know that from the theorem. So from the theorem that we had in the previous discussion, we have um, the absolute value of the sum, which is our natural logarithm 2, minus the sum of the first 8 series, okay, terms in the series rather. So you have s sub 8. which is just less than, okay, after the eighth element of the series, that's equal to 1 over 9. And since we're looking for the upper bound, if we are going to uh, if we're going to translate this one into decimals, then you have our 1 9 is of course less than, okay, this is 0.11, 0.111111, and so on. So the next of that would be 0.12. Okay, now to check, okay, we can use our calculator, okay, to get the sum of the first eight elements in the series. So you have, since you have 1 minus 1 half plus one third minus 1/4 plus 1 over 5 minus 1 over 6 uh, plus 1 over 7 minus 1 over 8. Using the calculator, you could have 533 over 840. Okay, thus, in this case, we can also use our calculator to check, okay, what is the exact value of the absolute value of natural logarithm 2 minus, you have our s sub 8 is 533 over 840, okay, which is approximately equal to 0.059. So this shows that the error is well under the estimate provided by the upper bound. Okay, so let's have the second example, and the next example rather. Find the partial sum that approximates the natural logarithm to one decimal place accuracy, the nearest tenth. Okay, so in this case, for our solution, okay, for one decimal place accuracy, we must choose a value of n for which we have the absolute value of our natural logarithm 2 minus our s sub n, okay, must be less than or equal to 0.05, because remember from the previous answer that we had, this this absolute value is equal to 0.059. Okay, so from the from the taken from the a theorem on the previous slides, we have the absolute value of the natural logarithm 2 minus our s sub n should be less than a sub n plus 1. Okay, so we could have, it suffice to choose n, okay, so that our a sub n plus 1 is less than or equal to 0.05. Okay, one way to find n is to use a calculating utility to obtain a numerical value for a sub 1, a sub 2, a sub 3, and so on until you encounter the first value that is less than or equal to 0.05. If you do that, you will find out that it is a sub 20 is exactly equal to 0.05. This tells us that the partial sum, which is the S sub 19, will provide the desired accuracy. Another way to find out is to solve the inequality. So what is that inequality? For this inequality, the inequality is equal to, the inequality is 1 over n plus 1 should be less than or equal to 0.05. Where is this taken? We are just get this one in our the sequence. Okay, the sequence. Okay, now take note. We can do this by taking the reciprocal, then reversing reversing the inequality, then simplify obtaining. Okay, so in this case, we just reverse the inequality. So you have n plus 1 is greater than or equal to 1 over 0.05, which is just equal to n plus 1 is greater than or equal to, using this one, this is equal to 20. And of course, in this case, your n must be greater than or equal to 19. Thus, our S sub 19 will provide the required accuracy which is consistent with the previous results. With the help of calculating utility, the value of S sub 19 is approximately, okay, equal to 0.7, and the value of, okay, our natural logarithm of 2, okay, obtained directly by approximating equal to, okay, from the previous results that we had, 0.69, which if we are going to round off this one to the nearest tenths place, then we could have, okay, this is equal to 0.7, which is the same with our S sub 19. Okay, so let's have the absolute convergence. So the series 1 minus 1 half minus 1 over 2 squared plus 1 over 2 cubed plus 1 over 2 to the fourth minus 1 over 2 to the fifth minus 1 over 2 to the sixth plus so on does not fit in any of the categories studied so far. It is mixed sign, but it's not alternating. So in this case, we will now develop some convergence tests that we can apply to such series. So we have here um, the definition. Okay, the series, the summation of u sub k from 1 to infinity is equal to u sub 1 plus u sub 2 plus so on plus u sub k plus so on. Is said to be convergence absolutely if the series is absolute values of the series, rather, if the series of absolute values, the summation of the absolute value u sub k from 1 to infinity is equal to the absolute value of u sub 1 plus the absolute value of u sub 2 plus so on plus the absolute value of u sub k plus so on converges, and said to be diverse absolutely if the series of the absolute values diverges. Okay. So let's have this example. Determine whether the following series converge absolutely. So you have 1 minus 1 half minus 1 over 2 squared rather plus 1 over 2 cubed plus 1 over 2 raised to 4 minus 1 over raised to 5, 2 raised to 5 minus so on. Okay, so the series of absolute values is a convergent geometric series. Okay, so the given series, of course, okay, this is actually taken from the previous examples that we had. Clearly, this is geometric, okay, convergent. This is convergent, okay, convergent geometric. We already have this one in our previous discussion. Okay, this is a convergent geometric series, which implies that since this is a geometric convergency, a convergent geometric series, okay, it also means, okay, it implies that the given series is a series that converges absolutely. Absolutely. Okay. So again, you have 1 minus 1 half plus 1 third minus 1 fourth plus 1 fifth minus so on. So the series is the series of absolute value is the divergent harmonic series. This is also we already calculated this one in our previous discussion. This is a divergent harmonic uh, harmonic sequence or series rather. Okay, which implies since this is a divergent harmonic series, which implies that the series is diverges diverges absolutely. Okay, so here another theorem. Okay, it is important to distinguish between the notions of convergence and absolute convergence. For example, the series in the previous example, okay, the previous example, converges since it is alternating harmonic series. Yet we demonstrate that it does not converge absolutely. However, the following theorems will show that if a series converges absolutely, then it converges. So if the series, you have the summation of the absolute value u sub k from 1 to infinity is equal to the absolute value of a u sub 1 plus the absolute value of u sub 2 plus so on plus the absolute value of u sub k plus so on converges, then so does the series, the summation of u sub k from 1 to infinity is equal to the u sub 1 plus u sub 2 plus so on plus u sub k plus so on. Okay. So example, show that the following series converges or converge. So observe that it is not an alternating series because the sign alternate in pairs after the first term. Thus, we have no convergence test that can be applied directly. However, if you can still remember with the previous examples that we had, uh, this series converge absolutely. So the theorem can be applied because in the previous examples, this is a geometric convergent. Okay, this is geometric convergent. Okay, since this is the geometric convergent, then we could say that the series is converge absolutely. Okay, so since the geometric convergent, the series is a geometric convergent. Okay, and it is also converges absolutely. It also implies that the series is convergent. Okay, so that is in the theorem that is being discussed previously. Okay, okay, so let's have this one. Show that the following series converge. In this case, we test the series for absolute convergence by examining the series of absolute values. So for our solution, we could have the summation of the quantity negative 1 raised to k plus 1 times k plus 3 over k times k plus 1, okay, from 1 to infinity. Okay, this is the same, okay, with the uh, summation. Okay, you have the summation of the absolute value of the quantity negative 1 raised to k plus 1 times k plus 3 over k times k plus 1, okay, from 1 to infinity. So by this, we just get the summation of k plus 3 over k times k plus 1 from 1 to infinity. Okay, so this suggests that the series of absolute values should behave like a divergent because in this case we have the concept of p series with p is equal to 1. So to prove that the series absolute values diverges, we apply the limit comparison test, okay, where we have our a sub k is equal to uh, k plus 3 over k times the quantity k plus 1, and we have our b sub k which is equal to 1 over k. So we obtain, okay, in this case, we obtain that we have the row is equal to the limit of a sub k over b sub k as k approaches to positive infinity, which is just equal to, we have the limit of of k times the quantity k plus 3 over k times k plus 1 as k approaches to positive infinity. In this case, we could have k cancel out the k, so you have the limit of k plus 3 over k plus 1 as k approaches to positive infinity, which is, this is equal to, you have, this is 3 k divided by k, so you have 1 plus 3 over k over 1 plus 1 over k. So that is 0. That is, yes, uh, okay, that is 0, 0. Okay, correct. That's equal to 1. Okay, so since the raw is finite and positive, it follows that the limit comparison test that the series of absolute values diverges. Thus, the original series converges and also diverges absolutely. So if this would be the case, we have converges conditionally. So this is an example of conditional convergence because the original series converges, but it's also diverges absolutely. So since we have a series, original series converges and also diverge absolutely, then we have a uh, conditional convergence. So the series converge conditionally. Okay. So let's have the ratio test for absolute convergence. Although one cannot generally infer convergence or divergence of a series from absolute divergence, the following variation of the ratio test provides a way of deducing divergence from absolute divergence in certain situation. Okay, so let's have this theorem. Okay, so this is the theorem for the ratio test for absolute convergence. So let the summation of u sub k be a series with non-zero terms and suppose that the rho is equal to the limit of the absolute value of u sub k plus 1 over the absolute value of u sub k from you have that must be as k approaches to positive infinity. Okay, there must be plus here. Okay. If the rho is less than 1, uh, then the series u sub k converges absolutely and therefore converges. If the rho is greater than 1, or if the rho is positive infinity, then the series u sub k diverges. And if p is equal to 1, No conclusion about convergence or absolute convergence can be drawn from this set. Okay. So let's have this one. Use the ratio test for absolute convergence to determine whether the series converges. So you have the summation of the quantity negative 1 raised to k times 2 raised to k over k factorial from 1 to infinity. So taking the absolute value of the general term u sub k, we obtain, okay, for the solution, we obtain that the absolute value of u sub k, okay, is equal to the absolute value of uh, the quantity negative 1 raised to k times 2 raised to k over k factorial, which is, okay, is equal to 2 raised to k over k factorial. Thus, by in this case, we could have the rho is equal to the limit of the absolute value of u sub k plus 1 over the absolute value of u sub k as k approaches to positive infinity. So in this case, we could have the limit of, we are just going to add 1. So you have 2 over k. So you have 2 raised to k plus 1 over the quantity k plus 1 factorial all over, you have uh, 2 raised to k over k factorial as k approaches to positive infinity. Okay, so in that case, we have the limit of 2 raised to k plus 1 over the quantity k plus 1 factorial multiplied by k factorial over 2 raised to k as k approaches to positive infinity. In this case, since we multiply the reciprocal, then we can have, we can, um, we can simplify in this case since you have 2k plus 1, so this can be expressed as 2 raised to k times 2. So in this case, the k can be, the 2 raised to k can be eliminated or divide out. And then here you have k plus 1 factorial, so that is k plus 1 times k factorial. So here the k factorial can be divided out. So what remains is you have the limit of 2, because this one can be expressed as 2 raised to k times 2, and this one can be expressed as k plus 1 times k factorial. So over, you have k plus 1 as k approaches to positive infinity. So in this case, the limit of this one is equal to, so 2 2 over k, that is 0. Okay, here you have uh, 1 1 plus 1 over k, so that's 0. So 0 divided by 1 is equal to 0. So as we can see, our rho is less than 1, which applies that the series converges. So in this case, we can say that the series converges. And since the series converges absolutely, okay, the series absolutely. So since the series converges absolutely, it implies that the series, okay, converges. Okay, so let's have another example. So use the ratio test of absolute convergence to determine whether the series converges. So in this case, you have the summation of the quantity negative 1 raised to k times the quantity 2k minus 1 factorial all over 3 raised to k from 1 to infinity. Okay, so in this case, we take the absolute value of the general term u sub k. So we obtain for our solution, so we obtain that you have uh, the absolute value of u sub k is equal to the absolute value of the quantity negative 1 raised to k times the quantity 2k minus 1 factorial over 3 raised to k. So in this case, okay, taking the absolute value of this one, we could have this can be eliminated. So you have uh, the quantity 2k minus 1 factorial over 3 raised to k. So in this case, then we could have our rho. So the rho is equal to the limit of you have the absolute value of u sub k plus 1 over the absolute value of u sub k as k approaches to positive infinity. So in this case, since this is 2k and then plus 1, what you have is limit of you have 2 times, let me check. So this is, you have uh, 2 times k plus 1 minus 1, this is factorial, over 3 raised to k plus 1, all over you have the quantity 2k minus 1 factorial over 3 raised to k, where k approaches to positive infinity. So this is just the same with the limit of uh, you have 2 times the quantity of k plus 1 minus 1 factorial over 3 raised to k plus 1 multiplied by 3 raised to k over you have the quantity 2k minus 1 factorial as k approaches to positive infinity. So in this case, we can now simplify. We can simplify here the limit of you have 2k plus you have 2 minus 1 is 2. 2 minus 1 is 1. Okay. Factorial over you have this can be expressed as 3 raised to k times 3 multiplied by 3 raised to k over you have the quantity 2k minus 1 factorial. So in other words, we can divide out in that case. So you have as k approaches to positive infinity. So here you have the limit of 1/3 multiplied by you have uh, 2k plus 1 factorial over the quantity 2k minus 1 factorial as k approaches to positive infinity. So this is just the same. We can have here 1/3 times the limit. We can express this one, we can expand this one. So you have the quantity 2k plus 1 times you have 2k times you have 2k minus 1 factorial. all over you have the quantity 2k minus 1 factorial. So as k approaches the positive infinity. So in this case, we could have one third of the limit of you have the quantity 2k plus 1 times 2k as k approaches to positive infinity. So simplify using you have the concept of this one. So this is equal to positive infinity. So which implies that the series diverges. So here we could have the series diverges. So that's end our presentation on this concept.